So I wanted to really quickly go through the solution to this last homework with you all. I'm going to hand out a hard copy right now. Most of you all, arguably, I mean, the results were pretty good. I don't think there were too many glaring conceptual questions. I do want to talk about number 4 a little bit because I think it maybe, I don't want to say confused, but I think there's some worthwhile discussion there. 1, 2, 3, 4, 5, 6. There's that. All right. So a little bit of bookkeeping. So your grades are on MU Online. They haven't been turned on yet. I wanted to give you the homework back first, but I'll turn those on later on today. So real quick, these solutions basically just come straight out of the solutions manual. And I mean, I think for problems 1, 2, and 3, there's not a terrible amount to say because I think arguably everybody did pretty well. Now the book tends to do everything in symbolic format. You know, they derive an equation, then they plug and chug. But arguably a lot of this stuff should be pretty basic. For instance, problem 1, we had an example that was really close to this in class, so I don't think there were too many significant issues. If anything, calculator errors, units, rounding, you know, stuff like that. Problem 2, the big thing was just recognizing that the cross-sectional area changes from one segment to another, to the solid segment versus the hollow segment. So it's just keeping track your amount of stretch in each segment. I think all in all, everybody did pretty well on that. Let's see, problem 3. This was just, this was similar to that one example that we did. Well, actually, no, this is more really just a statics-based section. You know, you have a hinge here, some moments here to determine the force in that cable, and then from there, stress and strain. I think it was, all in all, pretty straightforward. Number 4, I do want to spend a little bit of time talking about. So number 4, you were given a set of load and elongation data. I'm actually going to pull up my Excel sheet so that you all can see what's going on with that. Let's see, homeworks. All right, so here's my Excel sheet. Let me zoom in a little bit so everybody can read that. So this set of orange data here on the left, this is what was given. So the loads and the displacements. So the first thing that I do is I input the area and the length. Now, if you want, you could just put a single cell of area and length and then just lock it with F4. I'm sure you all have had engineering computations and you've done this, something like this before. But if it's been a while, no big deal. I just sort of input this in everywhere. I didn't really want this to be an Excel class. So to compute the stress, I just take P over A, and to compute the strain, displacement over the original length divided by 2. Now, what I did just to keep everything manageable, I turned the stress into KSI. So how did I go from this column to this column? I just divide by 1,000. Okay. Now, a couple things. So let's talk about some of the data that you would interpret from it. So E. E is the modulus of elasticity, which is the slope of this region. And some of you were doing like a linear interpolation, you know, trying to get an R squared, you know, mx plus b, and trying to get the slope of the whole thing. Now that's not the case. We're only talking about this region right here. So an easy way of doing that is just to pick, I don't know, a point maybe like right here, you know, near the top of this linear region, somewhere about right there. And then just say, okay, let's say I highlighted that, and maybe you can kind of read this. I've got a stress value of like 59.9 KSI and a strain of 0.00195. Just take stress divided by strain, and you should get something around 30,000. So the textbook listed the solution as about 30,000, you know, roughly equal to. Anything around that should have been fine. Now, the proportional limit is where it starts turning nonlinear, where that yielding begins. So what I've got here is I've got 2 stress strain curves. It's literally the exact same curve, only I kind of zoomed in on this region here where it starts to yield. You can kind of see it starts to veer away from that linear portion right around here, which is around 65 KSI. So that's where that proportional limit comes from. Now, how do you get that 0.1% offset? You need the E value So once you get an E of 30,000 KSI, you plot another line offset at a strain of 0.1% or 0.001. Draw that line and then zoom in to see where it intersects. Now if you zoom in, you can kind of see that intersects somewhere between 68 and 70. So the textbook listed 69. That's where that came from. Okay? And lastly, the ultimate stress, literally just the maximum stress that you read. So I can just go to the table and see that's 112.83. So that's pretty straightforward. Okay, does anybody have any questions on this? All right, a couple things I just wanted to point out just in terms of bookkeeping. So, I mean, like I said, you all did very well. I mean, the average was like an 88, so that's pretty good. A couple things, formatting. Okay, I told the TA to just ignore formatting requirements for this one, just to give you all a, a second chance, if you will. I mean, it's really basic. Just make sure you're using the original assignment as the cover sheet. A lot of people didn't have cover sheets. Quad paper and engineering paper, no notebook paper or anything like that. You use either graph paper or engineering paper. Clean handwriting, make sure you're using a straight edge. Make sure you're clearly boxing or marking your answers. Everybody good? All right, now another thing, there was a couple folks in here that I could tell, and the TA could tell that you had the international version of the textbook. And that's fine, I don't have an issue with that, but the problems are different. Some of the problems are different. I think it was number 1 and number 4, the problems are different. So what I did was this, is I just graded those problems, assuming everything was correct, and then gave you credit accordingly. But next time, from here on out, make sure you're responsible for the problems. Again, the material in the textbook's the same, so the international version's not an issue, but make sure the problems match. Everybody good? And lastly, I'll just go ahead and throw this out there just so everybody's clear, and I don't mean to throw in too much unpleasantness, but I am fully aware that there's this thing called the internet, and there's a vast number of things on the internet, including the solutions manual. I know that it was used on this assignment by some folks. I'll be honest, I don't remember who, but for instance, one that comes to mind, again, forgive me, I don't remember who, but I think it was like number 4. One student had like no calculations and just sort of came up with this image verbatim. There's no way they would have come up with this without doing a little bit of math. So, and there was no Excel to back it up either. So all I'll say about it is this, I'm aware that this stuff exists. I mean, heck, there are problems that I'll assign that you go to the back of the textbook and there's the answer. So, I mean, I'm fully aware of that. Will you do better on the homework? Well, yeah, if you've got the solutions, you'll do better on the homework, but you won't do better on the exam, okay? I'm just telling you, all right? So, everybody okay with that? Okay, all right. Sort of get all that out of the way. Okay, real quick, so before we get back to things, did everybody get a copy of their homework? Did everybody get their homework? Who didn't get it? Okay, all right. All right, what's your name? All right. I'm going to do better at remembering these names, I promise. By the end of the semester, I think I'll have everybody down pat. Okay, and did you get, you didn't get a solution? All right, did everybody get a copy of the homework and the solution? Okay, all right. So I'm going to go ahead and get the sign-in sheet started. So here's that. Okay, and let's go ahead and, all right. Before we get into the notes, today's, if you all recall in terms of bookkeeping, we have a homework assignment due on Thursday. So that's on our axially loaded members. Before I get into torsion, I do want to give you all a chance to ask any questions you have in relation to the next homework assignment. Does anybody have any questions? Everybody looked at it? All right. I actually have a few hard copies. Let's see, Mr. Ignatov, did you get one? What's that? Okay, hold on for one sec. Okay, I got Mr. Kuhn and Mr. Porter. Oh, sorry. Okay. What was the question? Sorry. Okay. Do you have the? I didn't bring the textbook with me. Do you have? Here, you find that real quick. You'll be past that. What problem? 2, 4, 5. Okay, this one. Okay, so, all right. So help me out. What's the question? If you don't mind me. What's the question?
Yeah, I don't like
Okay, all right. So problem 2, 4, 5, just so everybody's clear, is the second problem on the homework assignment, and it's the problem that involves the weight attached to 3 cables. And what I will say is this. This problem is essentially the same thing as that composite column, because you've got an axial load supported by a column. In this case, it's a cable, but it's the same deal, supported by a column of 2 materials. One of the materials is, oh, no. Sorry. Never mind. I'm thinking of a different problem. Apologies. No, okay, so everything here is steel. Okay, so this should be pretty basic. Okay, so in terms of math. So you've got a load that's supported by nothing but steel cables. So what you should be able to do is determine the area of all those steel cables, and then load divided by area will give you stress. Make sense? Okay, so let's see. Wait. Weight of the load. Now I'm going to read it so that I make sure I'm telling you the right thing. Diameter of middle cable. Okay. All right, weight of the load is increased by 9 kips to 21 kips. What percent of the total load is now carried by the middle cable? Well, for part A, unless I'm reading this incorrectly, it would still just be 33%. The stresses would be different. Okay. All right. So with problem 2, okay. So the deal with problem 2, you've got the same load supported by 3 cables, but the cables have different areas. So you have the same force on each cable, but it's all about what are the stresses on each cable, because stress is force divided by area. So while you might have the same force, you're going to have different stresses because it's load divided by area. Does that make sense? Tell you what, I'll do this. Let me go through it, and because I want to yield time for this, I'm going to go through this, and I'll make it simple. I'll just email out sort of a couple hints to everybody in the class. Is that fair? Mm-hmm. All right, because I don't want to sit here for 10, 20 minutes and, go through this. But does that sound good? I'll just go through it and make sure I got my ducks in a row, unless there's something I'm missing. So, all right, sound good? All right. Anybody else?
Number 3, the hint you gave.
Let me see. Yeah.
Where you said assume A is free.
Mm-hmm.
Do you mean like assume there's no force there at all?
No. That's something. Okay. So the question is on number 3. Goodness. 2.4 dash what? 9. Okay, I'm looking at this upside down. Okay, all right. So 249 is a problem that looks like this. Okay, so you've got a sort of a pipe in series that's supported on the top and bottom. Now, if I take this load P and I push there, I'm going to generate a reaction, a force at both places. But I don't know how much. Like, I don't know if it's, half and half, if it's, 25%, 75%. I don't know the distribution because it's indeterminate. There's 2 unknowns, but there's only one equation of equilibrium, just the forces going down in that direction. So what I'm going to do is I'm going to assume that A is free. Now, what I mean when I say I assume A is free, I mean it's free to displace. Okay? So imagine that this support A is gone. Now, if I take this load P and I push right there, what's going to happen to point A? It's going to go down, right? So it's going to go down, let's make up a number. Let's say 2 inches. Okay, so let's say it displaces 2 inches. I'm then going to say, okay, given this series of pipes, how much do I have to yank up on it to pull it up 2 inches? And then whatever that value is, that's going to be the reaction at A. Then I can use equilibrium to get the reaction at B. Does that make sense? And that's going to be the deal with any type of indeterminate problem, is you're going to employ a compatibility relationship. And in this case, the compatibility relationship is that the total displacement at A is 0. You could do the same thing for B, too. You'd get the same deal. Yes, sir?
So let's say you find the deformation of that part that you assume to be 3,
Yes.
and then you want to pull it up. You do deformation equals PL over EA.
Mm-hmm.
Substitute in the value for deformation, and then solve for
There you go. There you go. So let me sort of draw that on the screen to make sure everybody's clear on that. All right. So what is it? Problem 3. Okay. So it looks something like this. We have a bar that looks something kind of like this, and we're taking this and we're pushing on it like so, right? Okay? So what I'm going to do is I'm going to do 2 problems. Now, the first problem is going to look like this. Okay? And I'm going to have all my original loads on here. Now that could be mechanical loads, it could be thermal loads, everything that was originally on the shaft. Okay? Now, once I push down, this is going to deflect some. It's going to go down some amount delta. So let's say delta is 2 inches. Make sense? I'm just making up the 2 inches. Don't take that to the bank. Okay? Now, one thing I will point out, let's sort of make sure we're clear on stresses. What's the stress in this lower segment over here? It's going to be P over A, right? Or whatever. What's the stress in the upper segment over here? It's 0. There's no load in this segment. That doesn't mean it doesn't displace. This part's going to shrink too. This is just going to go along for the ride. Does that make sense? So I propose to you that to get this displacement, it's going to be PL over EA of that segment alone. Because technically you would add the PL over EA on the top segment, but there is no load. That make sense? Okay. So that's sort of scenario 1. I get some displacement. And then what I do afterwards is I say, all right, let's look at scenario 2. And scenario 2 is looking at the same bar, kind of like this, but I'm going to yank up on it some. Now I'm going to yank up on it to produce a deflection in the opposite direction of 2 inches. Okay? In other words, that if I take these results and I superimpose them with these results, I get a total deflection at this point of, well, no, of 0, right? Because this is going to go 2 inches down. If I pull this 2 inches up and add those results together, this point moves a net of 0. Make sense? Okay, all right. Now, here's the thing with this segment. Okay? So we're going to pull some with some force P, right? Make sense? Now, this segment here is going to have a stress. It's going to be what? P over, what do we call that? A1. This segment is also going to have a stress, P over A2. So to calculate the total deformation on this bottom segment, I've got to add, P L1 over E A1 plus P L2 over E A2. And then, that's going to be equal 2 inches, and then solve for P. So the idea is this. On this lower situation, if I apply a load here, I've got a force in this pipe and a force in this pipe. On the upper situation, I don't have any force, bless you, I don't have any force up here. Does that make sense? It's just all about maintaining your equilibrium. It's the same tricks we've been using this whole time. You know, cut a section, determine the forces in each component. Make sense? All right. Anybody else have any questions? All right. Let me think about that problem too, because right now, for some reason, I don't know if I'm missing something, but I want to make sure I'm doing my homework on that. All right? No pun intended. All right. Everybody good? Please, and if you got any other questions, please. Anybody else? I mean, this is good stuff. I think number 4 was kind of the same story. You do the same thing. Although I think number 4 had a thermal load on it, didn't it? Number 4 was a temperature variation. Everybody good? Any questions? Okay. All right. Then let us continue to the topic at hand. Let us talk about torsion. Now, before we get into this, I'm just going to prepare you right off the bat. You're going to see some math here. We're going to do a big derivation. So there's going to be a lot of math, a little bit of calculus, a little bit of that. It'll be okay. Just breathe. Okay. I'm just preparing you for that because I don't want you to just see this and go, oh, goodness. I mean, I understand the tendency. I do. Some of this stuff is important, but I'm going to do my best to sort of keep everybody on pace and keep everybody involved. Because this derivation for torsion is going to be much more involved than what we've dealt with before. But the interesting thing about torsion is, remember that conclusion that we made last time, that if you're talking about a bar that's being yanked on, you know, or pushed on, that axial deformation is PL over EA. For torsion, the total angle of twist is going to be TL over GJ. Now, the reason why we cover this, now I know you're like, oh, I don't really follow because we haven't gone through the derivation. But when it's all said and done, you're going to see a lot of similarities. I mean, a lot of similarities between what we do for axial loads and what we do for torsion, which is why it comes next. Now, how we get there, that takes a little bit of discussion. So we're going to take this slowly, but because I think it's so important, I want to make sure everybody's following along. So just so we're clear, the problem at hand, what we're going to be discussing is torsion. In other words, taking a bar and twisting it and trying to determine the resulting displacement, which I think it should be clear, if I take a bar and I twist it, it's not going to get longer or shorter. That's not what we're after. If I take a bar and twist it, what I'm going to get is a change of angle. Okay? Make sense? So our goal is to try and determine that change of angle. Okay? So everybody's clear. Okay? Now, I mentioned this last time, but I want to be very clear. I will never, in this course, give you a torsion problem on a section that is non-circular. Never. Okay? I teach, as far as I know, assuming the schedule goes well, next semester I'm going to teach a graduate level course called Engineering 670. It's called Advanced Stress Analysis, but basically it's Mechanics of Deformable Bodies 2. And in there we will look at, well, how do you deal with torsion on non-circular sections? And it's not, I won't say it's difficult, it's just really involved. You have to be able to assess a phenomenon known as warping. And what warping is when you apply torsion to a section that's circular, all it does is rotate. Its angle changes, and that's it. But if it's non-circular, just because of the physics and the way that these things respond, non-circular sections, they not only rotate, but they deform in and out of the plane. Okay? So if I have like a square block of foam, and you can find these on Google, you know, images of this all over the place, but if you have a square, let's say, block of foam, and you draw a grid on it, and you twist it, that grid will actually deform in and out like this. That doesn't happen with a circular section. It remains planar. Okay? But with square sections or anything that's non-circular, they deform in and out of the plane. Like if I cut a section and I look at it like this, like it's a sheet of paper, it's actually deforming like this. And it makes the response and the math a little more difficult. It also, in many cases, makes the response undesirable. And we mentioned this last time. If you're designing some machine part that's going to be twisted, the last thing that you want is for it to warp, because it's going to induce additional stresses into whatever it's connected to. You mechanical engineers who are designing mechanical components can almost guarantee you 999 times out of 1,000, if you're designing something that is meant to be twisted, it will be circular, okay? Because it's going to respond in a predictable fashion, okay? It's going to be easier to fabricate, easier to put together, and things in torsion are circular. Let me say it like this: circular segments respond to torsion in the best fashion. They're the most efficient shapes to resist torsion anyways. So, okay. Everybody good on that? Okay. Now, one of the points I want to make behind what it is that we're going to discuss is what torsion looks like on a circular shaft. In other words, before and after. So if I've got some circular shaft, and this could be a solid shaft, it could be a pipe, it doesn't matter. And let's say I draw like a nice little rectangular grid on it, and I isolate one of these little elements. I've got this shaded in blue, just a little element. And this is sort of a before and after thing. So before and after, here's what the segment looks like before deformation, and here's what it looks like after. Now, the shape moves, obviously, but what I'm really after is the deformation. And the way it deformed is it underwent an angle change. And we've mentioned this before. I'm going to go back a little bit. We've mentioned this before. When we first defined the concept for strain, I mean, let's go back to, this is almost like day one, day two when we talked about strain. Axial strain we defined as a percent elongation, a change in length divided by the original length. And it's sort of again, a percent elongation. That's normal strain. Shearing strain, however, is not about a change in length. It's about a change in angle, okay? So when we're talking about shear, we're not interested in change in length. We're interested in change in angle. And that's very obviously what's going on here, so that's what we need to be able to capture. So instead of dealing with things in normal stress and normal strain, let me go forward a little bit. Instead of dealing with things in normal stress and normal strain, we're going to be dealing with shear stress and shear strain, okay? Make sense? All right. So let's get into it. Okay, so what I'm going to do is I'm going to look at a segment, and I'm going to cut out a little element, a little differential element. And this is a really common way in our field to try and investigate what's going on. Because if you can define what's going on your small little differential element, and then if you can integrate, you can determine what's going on for the entire shaft. So what we're going to do is we're going to try and investigate this little element. Now what I've done is I've cut out a small little segment, or a little disc of the shaft, if you will, and I'm going to investigate a little element of this disc, that little shaded blue section there at the center. Everybody good? Now, one variable I'm going to define for you, just so we're clear on our coordinate systems. Let's start off with the x coordinate system. So x is going to run along the shaft. So our range, if you will, would be from x equals 0 to x equals L, however long the shaft is. Make sense? Let's also look at rho, this little P-looking thing, the Greek letter rho. Okay? So rho is going to define our radial dimension, how far away from the center of that shaft that we are. So rho is a variable. It's going to go from rho equals 0 to rho equals r, whatever the radius of the section is. So if it's a 4-inch diameter shaft, it would go from 0 to 2. Make sense? Everybody good? Okay. So let's zoom in. So I'm taking this little element and I'm zooming in. Okay. And just like before, I'm looking at a before and after picture of what's going on. Okay. Make sense? Now this is a super, super tiny little segment, so let's be clear on its dimensions. This segment is dx long. Now why am I doing dx long? Because x is along the segment, so that little disk is dxy. So ultimately I would want to integrate from 0 to L for x, along the x coordinate. Make sense? Now, like we also said, when we're talking about shearing deformations, particularly in this case with torsion, we're talking about a change of angle. So I probably should have a right angle included here on the left side as well, but I don't think it's as pertinent. Over here on the right, this is sort of before and after deformation. And really what we're after is this change in angle. Okay? This is sort of what we're after right here. Let me see if I can... hold on, let's see. We're really after this change in angle right here. Okay? Make sense? Now, one thing I'm gonna throw up here just so everybody's clear. Let's go back to, I don't know if this is high school geometry or Math 132, somewhere in the middle. But you all have probably done problems like this before. You've got a circle, you know, like this, and let's say you've got, you know, some angle, something like that, and then this dimension is r, right? Okay. How do you determine this arc length? R theta, right? Because if you went across the entire circle, you'd get 2 pi r, and that would be the circumference, right? Everybody's seen that before, right? Everybody okay with that? Okay. All right. All right. You want me to leave that up here for a second? I see a couple folks writing that down. You want me to leave that up? Okay. All right. Okay. The reason why that's important is because I want to take a look at this little arc length, and I'm going to call that S. Okay? So I've got this little arc length here, S. How am I going to define that? How am I going to calculate that? Well, I can look at it 2 ways. Okay? One of the ways is I can say, you know, that R times that angle right here, and I can say gamma dx, which gamma is really what I'm after. Okay? So I can look at it from the top of the segment. Another way I can look at it is from the side. I can say R times my change in angle, right? So is everybody seeing how I'm just able to say that rho d phi equals gamma dx? All right? Make sense? Or phi, if you will. Phi, phi, however you want to say it. Faux fum. All right. Okay. So rearranging that a little bit, I can get that the shear strain, gamma, is my distance from the center times the rate of the angle change. Because that's what d phi dx is. It's how fast the angle is changing along the length with respect to the length. Make sense? All right. So let's take that equation one step at a time. Let's see what it tells us. Okay, it tells us a couple things. It's telling us that the strain is proportional to the distance from the center of the shaft. In other words, the farther away I am from the center of the shaft, the more strain I'm going to get. So if I take, let's say, a solid circular shaft and I twist it, the amount of strain at the dead center is 0. Make sense? It's not deforming at the center at all. But the farther away I get from the center, the more deformation I get. Make sense? Okay? So that's going to help us out. All right? And since we're assuming that, at least for much of our designs, that everything's linear, remember we had that stress and strain were related through this thing called Young's modulus, the modulus of elasticity? Well, similarly, shear stress and shear strain are also related through a shear modulus. Okay? Just like, you know, steel has a Young's modulus and brass has a Young's modulus and aluminum has a Young's modulus, same thing with G. Steel has a shear modulus, aluminum has a shear modulus, brass has a shear modulus, and what have you. That's easily looked up. Nice little material property we can look up. So that helps us out quite a bit, okay? Because if we recognize that things are proportional, we can make the following observation. So let me sort of take this one step at a time and sort of digest it. Which, by the way, if you're wanting the whole big picture at the very end, don't worry. I've got a nice couple slides that just, there's all the formulas you need. So don't worry. If the derivation's like, oh my goodness, don't worry. Don't worry. It'll be all right, I promise. Okay, so let's look here on the left. So on the left, we've got the same thing I said earlier. Rho is my variable. It's telling me how far away I am from the center. So rho is going to go anywhere from rho equals 0 to rho equals whatever r is. Okay? What I'm proposing is that based on the way that this thing's going to deform, the stress is going to be linear, okay? I mean, and I think if you think about that and reason through that, that kind of makes a lot of sense. I mean, if I take a solid segment and twist it, the center isn't going to deform at all. Well, if it's not going to deform, it's not going to generate any stress, right? And if I get most of my deformation at the very, very top on the outside of the shaft, that's where I'm going to get most of my stress. You know, stress and strain, they're related. So I propose to you that the stress is linear and that the most stress I get in a torsional segment is on the very outside. I don't get any stress in the center at all. And it's linear. So it's from, you know, tau equals 0 to tau equals some maximum value, tau max. And we'll talk about what, you know, how to get that here in a second. So I'm saying that tau, this is my stress profile. I'm saying it's, you know, tau max times rho over r. And if you're wondering how I'm getting that, it's basically just y equals mx plus b. What's my my intercept? At the center it's 0. And what's the slope? Change in y, or in this case, change in stress divided by change in radius. So that divided by that times x, or rho in this case. Make sense? Everybody good? And if it does, just plug in values. What's the stress at rho equals 0? It's 0. What's the stress at the edge? Rho equals r. It's just tau max. Make sense? Okay. All right. How's that going to help us out? Well, if we can figure out what tau max is, we got it down pat. Okay. Now, the way I'm going to do that is I'm going to do a little bit of equilibrium assessment, but in order to do that, I need some section properties, so I need an area. Now, we ought to know how to find the area of a circle. It's just pi r squared, or pi d squared divided by 4, right? Okay. What I want to look at is if we need to integrate over the area. So what I'm going to do is I'm going to calculate the area of a little ring, a little ring of that cross section, and then I'm going to integrate across the whole thing. Now, how would I calculate the area of that little ring? Well, it's pretty easy if you think about it, because all it's going to be is the circumference times the thickness. Make sense? So what's the circumference of a circle? It's 2 pi times the radius, or 2 pi times wherever this ring is, rho. And how thick is it? It's a little differential element, a little tiny element. It's d rho thick. Make sense? Now, if you don't believe that that'll work, just do this. Just say, all right, integrate from rho equals 0 to rho equals r, that, or rho equals 0 to rho equals r of 2 pi rho d rho, and see what you get. What do you get? Well, 2 pi is a constant, right? So we pull that on the outside. And then what's the integral of rho going to be? Like, what's the integral of x? X squared over 2, right? So this is going to be rho squared over 2 from rho equals 0 to rho equals r. And what is that? The 2's cancel, and I get pi r squared, which is the area of a circle, right? Make sense? So everybody's convinced that this is valid, what I'm doing up here, right? No. I'm talking about a very tiny slice, a differential slice, if you will. So dp is the thickness, or d rho. I know that I have a tendency to say dp too, but we're talking about the thickness. Okay, so if I've got some, if I'm talking in rectangular coordinates, and I've got some, body out here, and I cut out a little segment, I would say it's, dx wide by dy tall. See what I mean? So just that little distance. All right, so far so good? Okay. I'll just leave that there for now. All right. Everybody good? Okay. All right. So what I'm doing now is a little bit of equilibrium assessment. So if I've got the area of this little ring, how do I calculate the force on this little ring? Well, stress is force over area. So if I take the area of this little ring, multiply it by the stress, that'll give me the force, right? So far, so good? Now, what about torque? How do I get torque? Well, torque is basically a moment. And how do you calculate moment? It's force times distance, right? So if I take this force and multiply it by the distance, in this case the distance from the center row, I got the amount of torque. Make sense? I'm talking about differentials here. I'm talking about the amount of force in that little segment, so dF, the amount of torque in that little segment, so dt. So far, so good? Okay, all right. Now, what am I doing here? It's just a little bit of plug and chug, so let's follow through, okay? So we had that dA was 2 pi rho d rho, and we had these expressions here. So here's the stress formula, which we generated earlier, that linear stress profile. Here's the area. So how do I get the force? That times that, and that's what I've got. How do I get the torque? That times that. So this is just plug and chug, and I ultimately arrive at this. Everybody good? Okay, there is a reason why I'm going about this, and you'll see this here shortly. Okay. Now, if I'm interested in determining the torque across the entire section, I would just integrate that, okay? And again, I'm still dealing with my variable as being rho, okay? From, the bottom, or from the center of that segment out. So I'm integrating from rho equals 0 to rho equals r. So long and short of it, I get an expression that looks like this. Okay. Now, why is that important? Okay. I want to pay attention to everything that's going on inside this set of parentheses. All right, everybody see that? Okay, let's highlight that out. It's 2 pi times the integral of rho cubed d rho. Okay. I propose to you that what's going on inside that integral is a section property. And what do I mean by section property? A section property is something like area. Okay? In other words, if I have some bar and I use my secret weapon, samurai sword and or lightsaber, I cut a section through that bar and I look at that bar has certain properties. Okay? Let's say it's a circular bar. That circular bar has certain properties. For instance, it has an area, right? Pi r squared. It has a centroid, right smack dab in the middle of the circle, right? Make sense? That shape has certain properties, or that cross-section has certain properties. Hence, we call them section properties, okay? I propose to you that this quantity inside the parentheses is a new section property. It's something new, something you haven't seen before, but it is just as feasible of a section property like any other. Just like area and what have you, just like centroids. You all have heard of centroids before, right? Just like area and just like centroids, this is a new property. Now, I propose we call this property J, okay? And J stands for what we call the torsion constant, okay? And we'll talk about how we derive that here in a second, but if you look, we could actually go through and do it right now. All right. So far, so good? All right. Now, let's look at J. So I propose to you that J, like I said, is what's called the torsion constant. It's defined as the integral of rho squared over the area, which if you go through and plug and chug your coordinates, you're going to get this. Now, for a circle, J is really easy to compute. You just go through and do the integral, and you'll get pi r to the 4th over 2, which r to the 4th might seem like an odd section property. How are you taking inches and raising them to the 4th? Well, that happens. J is a very, it does. It's all about, sort of taking area and squaring it, if you will, that squared proportional distance. J is a quantity that's going to be in inches to the 4th. There's going to be a very important quantity we're going to mention later called a moment of inertia. Did you all do moments of inertia in statics? A little bit? Okay, all right. We'll do them a little more in depth in here. But if J, let me just say this real quick. If J is a relation, if you will, of torsional stiffness, how much something resists torsion, the moment of inertia is a measure of how much something resists bending. Just as A is a measure of how much something resists axial load. I mean, think about it like this. If I have a bar, the bigger A gets, the area, the tougher it is to stretch or contract. Make sense? Same thing with J. Yes, sir.
So is this what's used to determine section modules for beams? Because I know units are usually
Well, okay. Section. All right, so that's a good question. So what's the deal with section modules? Section moduli are something we're going to talk about much in great detail later. A couple things though. A section modulus is actually an inches to the third. That's number one. And number two, section moduli are direct. Their direct application is in bending. In other words, if you take the bending moment and apply, if you have the bending moment on a beam and you divide that by the section modulus, you'll get the maximum bending stress. Now, it's a little more involved than that because you can have different section moduli if the shape isn't symmetric or what have you. So it's a little more involved. But we're on the right path. Make sense? Okay. Now, so the nice thing about J is we can get nice little plug and chug formulas, and I've provided those right here. So if you have a solid shaft, J is pi r to the fourth over 2. Or if you're like me and you like to deal in diameters, it's pi d to the fourth over 32. Now where did I get the 32? R is d over 2, and I take d over 2 and I raise it to the fourth power. 2 to the fourth is what, 16? And 16 times 2 is 32. Now, if you're doing J for, let's say, a pipe, you just take the J of the outside minus the J of the inside. So that's really what's going on here. It's the same deal. Same thing with area. You can take the area of the outside minus the area of the inside. So far, so good? Okay. So J ultimately is going to make our formulation incredibly easier, okay? Because now we're able to determine the stress quite easily. Because what we were trying to do is look at tau max. We were trying to determine what tau max. Well, instead, what I found is the entire distribution. So I can find tau max pretty easily. It's just TR over J. All right. So lastly, a couple things. So let's see. Remember that we've got this relationship between stress and strain. We call that the shear modulus, that value G. So we can plug that in and we can get a determination of shearing strain. Instead of shear stress, we can get shear strain, what's the difference between shear stress and shear strain? Just dividing by G. That's all it is, just dividing by that shear modulus. And obviously, of course, the maximum shear strain is going to be at the very top. Now, if I want the angle twist, the change in angle, I've got to take into account the length. In other words, if I hold the shaft here and I twist it, I'm going to get much more deformation here where my hand is twisting it than I am here at the end. I mean, and think about that. That should make sense if you think about it. I mean, if I've got a strong grip on this shaft and I take it and I twist it, I'm getting a significant amount of twist over here on my right hand. But my left hand, it's not twisting at all, right? Make sense? So the angle of twist is going to change as a function of length. So how do I get that? Well, it's basically the same way that you got deformation in axial members. We determine that little bit of angle twist in that given element. So in this case, we've determined what the strain was. Now I'm going to back calculate what's going on with this little angle of twist, that d phi, how much it's rotating in this direction, and I integrate. Now if I've got, just like last time, remember we dealt with problems like this. If you have a constant load or a constant area, no need for the calculus. But if the torque varies, or if the load varies but the area varies, we had to integrate. Well, same deal here. If we have a constant torque and a constant cross-section, no need for calculus. However, if we got anything that varies, we got to go through and break out those integrals. Make sense? All right. So let's take a breath. The derivation's over. If you want, slide 85 in your handout. Put yourself a big star, here and on the next slide. Because the derivation is so involved, I decided to summarize everything in a nice, neat, concise little section at the end. So here's the summary of formulas. So shear stress. Okay, shear stress is linear from the center, and it's T rho over J. Okay, the maximum shear stress is at the end of the shaft or at the edge, TR over J. The shear strain, What's the difference between the shear stress and the shear strain? Just divide by G, so pretty simple. The angle of twist, technically I need to integrate, but if I've got a constant T and a constant J, it's just TL over GJ. So if you want, you can write that on the side as well, which I actually have that over here at the back, but that's okay. Now, J, I've got formulas for J for a solid shaft and for a pipe. One point to mention, your book calls J I sub P, okay? And the reason why it does that is because I sub P references what's called the polar moment of inertia, okay? I like to use J because J helps distinguish, in my opinion, what's going on between circular sections and non-circular sections. Later on, when you all are in your careers and you start, getting into the nitty-gritty of stress analysis and what have you, J is reserved, that symbol is usually reserved for pure torsion, just that twist, whereas warping is something entirely, and it's sort of, it's distinguished in that regards. Okay. All right. Now on the next slide, I've got the angle of twist is also, if you've got a constant torque or a constant J, is as follows, and for a given segment is just TL over GJ. All right. And last thing, I mentioned this last time, but I want to include it because this is one of my little curveballs I like to throw out here and there. What if I don't give you G? What if I give you E and the Poisson's ratio? How do you get G? You can compute it using the formula below. Now, I'm just giving that to you now. Next time, this is going to be much later on in the semester. We'll learn how we can derive this, okay? But that's another story for another day. For now, just believe me that formula works. So far, so good? Okay. So what we're going to do this time, and this will bleed over a little bit into next time, but I want to start off looking at some torsion problems. So I've got a segment that's 54 inches long. It's a solid steel circular bar. So we're going to be using J formulas for the shaft, not the pipe. Okay, the diameter is 1.5 inches. So we've got the steel E value and the Poisson's ratio. So we weren't given G. We're going to have to go and compute that. The bar is subjected to a constant torque. So this bar is subjected to a constant torque. So T is constant. Does J look like it's going to be constant? I mean, if I cut a section, am I going to get the same properties across the board? So what don't I need to do? I don't need any calculus, no integration. I got a constant T, constant J, no need to integrate. So I want to determine the following. If I've got a torque of 250 foot-pounds, what is the maximum shear stress in the bar, and what's the angle of twist between the ends of the bar? All right, that's part one. And if the allowable stress is 6,000 psi and the allowable angle of twist is 2.5 degrees, what's the maximum permissible torque? And this is a unique requirement. I haven't thrown this type of requirement at you before. But what I'm doing in this second bullet is I'm actually sort of throwing two caveats at you. In other words, I've got a maximum allowable shear stress. I can then back calculate, well, what torque would cause that? Now, I've also given you an allowable twist. I can then go back and say what torque would cause that. And from those two torques, you have to decide which is the more allowable one, that'll become clear here in a little bit. But that's sort of a somewhat new requirement. But that's something that you might have, very common, if you will, in the world of engineering. I can't tell you how many structural engineering problems we have where we design for moment capacity and shear capacity, but what governed our design, what dictated how large that beam would be, were deflection requirements. Beam was perfectly fine to resist the moment shear, but because it couldn't deflect too much, that's what limited the design. So that happens quite a bit. All right. Everybody good? Okay. Now, one thing I do want to point out before I draw this out, these arrows, this terminology, have you seen this before? You probably saw something like this in statics. If you ever see an arrow with two arrowheads like this, that indicates a moment. And for this class, usually the only time we will ever do that is for torsion, because this goes back to your right-hand rule. Your thumb points in the way of the torque, so we're saying it goes like this, right? And then this one goes like this. So it's almost like we're taking the bar and we're doing that to it. Make sense? So it's just an easier way to draw that. All right. So far, so good? All right. Okay. Example 11. All right. And again, I know that was a long derivation. It's not so bad, I promise. All right. So let's look at some given parameters. Let's see what we were given. Can somebody tell me a piece of information about the bar that we were given? Okay, we have the diameter. Okay, so let's start off with that. The diameter is what, 1.5 inches? Okay, so what can I do with that diameter that would be appropriate for a torsion problem? Well, we could find area, but with torsion, we don't really care so much about area. What do we care about? J. So we need J. And J for a torsional shaft, J for a solid circular shaft in torsion is pi d to the fourth over 32. Okay? So pi times 1.5 inches raised to the fourth, all divided by 32. All right, and that comes out to be what? I'm making y'all do math so early, goodness. There we go. 497? All right. And what are the units? Inches to the fourth. And that happens. It's okay. And you'll see how the units in the end, they sort of bear themselves out, and we'll be generating like PSI or KSI at the very end. Okay, what else were we given? The length. And the length of the rod is 54 inches. Okay, notice how I'm going to start to be pretty cognizant of the units. Okay, I'm going to start to be pretty aware of that. Okay, now, were we giving any properties in regards to the material? There we go. We were given an E value of, actually, let me do this. Let me be consistent. Let's put my L over here. 54. We were given E as what, 29 times 10 to the 6 psi, and we were given the Poisson's ratio is 0.3, right? So what can I do with that? G, which is, what is that? 2 times 1 plus nu on the bottom, and E on the top. 2 times 1 plus 0.3. And here I've got 29 times 10 to the 6 PSI. Again, I'm being diligent. I'm writing out the units, okay? You're going to want to do that. Be cognizant of that, okay? Anybody got a number for me? No, it's big. Let's just leave it at that. Just so I'm using enough decimal points so that we are aware of where it's coming from, but don't need to be any more diligent than that. So that's our shear modulus. Now, technically that's lower than the elastic modulus. The elastic modulus would be 29 million. This is only about 11 million. Materials will tend to be weaker in shear. It is what it is. And that'll become clear later on when we look at Moore's circle, but those are other stories for other days. All right, so far so good? Okay, let's look at part A. All right, now, what does part A say? Part A asks, if I have a torque applied of 250 foot-pounds, what's my stress and what is my angle of twist, right? Okay, so we have a torque of 250 foot-pounds, or torsion, torque. I'll be honest, I'll use the terms interchangeably. Anybody see a problem before we do anything? There we go. Units. It's not consistent with everything we got up here. PSI, inches to the fourth. We ought to convert that into inch-pounds. Now, how do I do that? Multiply by 12. We don't divide by 12, we multiply by 12, and that'll be 3,000. Okay? For some reason, I've noticed students tend to get a little confused on moments. I mean, just think of it as if it was feet or if it was inches. And how do you convert from feet to inches? You multiply. Okay? So that's 3,000 inch-pounds. All right, so far so good? And from here on out, it should be fairly plug and chug. So what would be the easiest way to determine the maximum shear stress? And just think of it like like what information are we given? What do we need to find? Well, what is our formula for maximum? What's that? Well, no, that'd be the angle of twist, which we're going to look at here in a second. TR over J, right? So TR over J, which we have all this information, right? We've got the torque, which is 3,000 inch-pounds. Now, the radius, we weren't given the radius, but I think we can figure that out, that's 1/2 of 1.5 inches. And we've got J now. J is 0.497. So that's all there is to it. And what do we get? $45.27. Now, what? PSI. So if you want, we can say answer A. Now, if you're unsure, how am I getting PSI? Look at the units, okay? So on the top, I've got inches times pounds times inches. So on the top, it's pounds times inches squared. And on the bottom, I've got inches to the fourth. So if I've got inches squared divided by inches to the fourth, that leaves inches squared on the bottom. So pounds over inches squared, PSI. Okay? So this is where I'm saying be cognizant of, your units. Be diligent. Write it out. Okay? So that might be another thing. That might be another justification as to why this unit comes out in inches to the fourth. It's so that the units resolve themselves, and so that the dimensions resolve themselves, and you get force per length squared for stress. Okay. Now, angle of twist. Now, we have a constant torque and a constant J. So how do I find phi max? And somebody mentioned this earlier. There we go. TL over GJ. Okay. So let's plug and chug. Let's see what we get. What do we got? On the top, we got 3,000 inch-pounds. The length is what? 54 inches. On the bottom, that big number, and then 0.497 inches to the fourth. Kind of, yeah. That's what I'm saying. Just like area is a property of that circle, J is one as well. And we'll derive more properties like a moment of inertia of a circle, or a section modulus of a circle, or a radius of gyration of a circle. It's just, you're exactly right. It's kind of like A, just another number that defines characteristics of that circle. Exactly right. Now, don't be worried if you get a small answer. Okay, that's okay. .0292, something like that, right? Okay, now, units. This is nifty. Okay, let's look at the bottom. What do I have? PSI times inches to the fourth. So that's pounds per square inch times inches to the fourth. So on the bottom, what is that? Pounds times inches squared on the bottom. On the top, what do I have? Pounds times inches squared. It's unitless when it comes to the canceling everything out. But how do you express the dimension of an angle with no units? Radians. Okay. So this is rotating 0.0292 radians. Now, how do I convert that into degrees? Well, a simple way of doing that is to say pi radians 180 degrees. A lot of people think 360 and 2 pi. That's fine. I do this because it's less number crunching on the calculator. And what do we get? We'll say 1.67 degrees. And while it's not technically required, I got to be honest, I got to convert everything into degrees just for my brain. I cannot think in radians. It's just the way my mind works. I can think in degrees. I understand 90 degrees is from here to here. I understand 45 halfway in between. I can visualize the degrees. I can't visualize radians. I'm sorry. Like a radian was like 57.2 degrees or something like that. I can't do it. So, all right. Sound good? All right. Any questions so far? All right. Now I think we can squeak out a little bit on this next part. So, let me. Can I go ahead and go to the next panel? Everybody got this written down? All right. So part B. Now, we're given two things. Let's handle each of these one at a time. Now, the first one says, okay, what if tau allowable is 6,000 psi? Which this should be a pretty reasonable thing to ask. You know, if I got this shaft, and I know it's made out of steel, so it's a particular grade of steel that I know this is the maximum amount of shear stress I'm going to allow it to carry. Maybe I should determine, well, what's the maximum amount of torque I can put on that to generate that. So how am I going to get that? I'm going to say, all right, it's kind of like what we did before. All right, we've got T, well, maybe I should go like this. Maybe I should say tau max is what? TR over J. So maybe I should rearrange. Would a fair way of rearranging that be that the maximum torque is going to be what? Tau allowable times J over R. Would that be a fair way of putting it? I mean, I'm basically just taking this equation, solving for T, so multiply that over, divide that down, and then solving for T, right? And what I would generate if I plug this value in, this 6,000 psi, that's the maximum amount of torque, the maximum amount of torsion that I can put on that shaft before I generate 6,000 psi. Does that make sense? Not too bad, right? Right. So, what is that? 6,000 psi. 0.497 inches to the fourth. And then what? Yeah, or 1/2 of 0.5 inches, or 1.5. So what are the units going to be? It's a torque, so it should come out like foot-pounds or foot-kips or inch-pounds, right? Because PSI, another way of looking at it, PSI times inches to the fourth is pounds times square inches. Divided by the inches, I get pounds times inches. So inch-pounds, whatever that comes out to be. All right? Plug and chug, and then that gives you, what is that? And we'll just leave it in whole numbers for now. 76. Everybody else get that? So think about that. I take this shaft and I put about 4,000 inch-pounds of torque on it. I'm going to hit 6,000 PSI, right? And think, everything's linear. So does that number make sense? I mean, go back to what we had before, okay? Before, we put 3,000 on there and we generated about 4,500 PSI, 4,527. So does it make sense then that to generate 6,000, we need about 3,976, a little bit more, right? And if you want, you can literally say, that 3,000 is to that 4,500 as some number is to 6,000. Just do it like that. It's the same thing. It's all linear. So does that number make sense? Okay, now let's do the second one real quick. Now the second one says, okay, we have an allowable angle of twist of 2.5 degrees. Now don't get me wrong, while I enjoy the degree notion, I like thinking of things in degrees, I got to convert that. So I do that and that comes out to be something about like that, right? I just got to do that right off the bat. All right? So now my question is, okay, to generate this allowable angle of twist, okay, what's going on there? Well, how do I calculate angle of twist? Well, it's TL over GJ, right? Okay, so if angle of twist is TL over GJ, would a fair way of saying this is T max is sigma allowable times what? GJ over L. Just taking this equation, solving for T, so move that on up, move that down, right? So plug and chug, and what do we get? Plug in that G value, 0.497 to the fourth, 54 inches. And before we do that, I'm actually going to box this answer, and then I'm going to box the answer below for a very specific reason. $44.86. Or no, it's inch pounds. Got a second? Okay, now, here's the big question of the day before we end things. All right, so the question asks, what's the maximum torque that can be applied? I'm limiting two things. I say the shear stress can't exceed 6,000 psi, and the angle of rotation can't exceed 2.5 degrees. It's the lower of the two, exactly. Because if I apply this much torque I'm going to get way more stress than 6,000 psi, right? But if I apply this, I'm safe on stress and I'm safe on the angle of rotation. Make sense? So this is where you have multiple design requirements and you got to go with the lower one. So therefore, T max is 39.76 inch-pounds. And if you want, you can convert that into foot-pounds, foot-pounds of torque. Maybe that's something and easier to understand. That's fine. I think it comes out to like 330 some foot-pounds of torque, something like that. All right. Does that make sense? That make sense? Anybody have any questions? All right. I'll check out. Well, give me some time. I want to check out what's going on with that problem. I want to make sure I'm giving everybody the correct advice, because I'll admit that right, without thinking about it, I might have to think about it myself. It just sort of hit me like a bucket of water, and I don't want to tell you something wrong. So that's all I got for today. I will see you all next time, and we'll continue on with torque. Don't forget, you got your assignment due Thursday.